Hi everyone, today we're going to be going over related rates. In Calculus AB, the most common examples are of a cone, a sphere, and a right triangle. So those are what we are going to be going over today. Let's get straight into it. So the first one I have here is a spherical balloon is inflated so that its radius r increases at a rate of 2 over r centimeters per second. How fast is the volume of the balloon increasing when the radius is 4 centimeters? Okay, so first of all, we are given that we have a sphere, and the radius of the sphere, so this distance, r, is increasing at a rate of 2 over r centimeters per second. So whenever you're given a rate or how fast something is changing, that means that you are given a derivative. So you're given a derivative of what you're trying to find. So this rate pertains to the radius, so it's going to be dr dt equal to 2 over r centimeters per second. So you're given here that dr dt is 2 over r. Now it also asks how fast, so another derivative, is the volume of the balloon increasing. So since you're given the derivative of the volume, you're trying to find dv dt. And then it gives you that the radius is 4 centimeters. So r is equal to 4 in this scenario. Okay, so now that we have our knowns and unknowns, we need to find a principal equation to really tie all of this information together. So we are given a sphere, so the volume of a sphere is 4/3 pi r cubed. And we want to derive this to find dv dt. So ddt of this equation is dv dt equals 4/3 pi times 3r squared times dr dt. Remember that this is implicit differentiation, so you want to use chain rule. Now dv dt is what we're trying to find. We have 4/3 pi times 3 times, so I'm going to leave r as a variable because dr dt has 2 over r. And so we can cancel the r out. And so we have, we can also cancel this 3 out here. So we have 4 pi r times 2. So we have dv dt is equal to 8 pi, and then r is equal to 4. So we have 32 pi. So 32 pi is our answer. And then for our unit, because we are given the volume, which we found the volume or how fast the volume is changing, we know that it's going to be centimeters cubed per second. So this is our answer right here. Okay, so the next one I have here is a conical paper cup is 10 centimeters tall with a radius of 10 centimeters. Okay, so I'm going to draw it out first. So the conical paper cup is 10 centimeters tall, and the radius is 10 centimeters. The cup is being filled with water so that the water level rises at a rate of 2 centimeters per second. Okay, so the water here, the water level, I'm going to call that H. It rises at a rate of 2 centimeters per second. So we're given another rate that is the derivative of H, or the water level. So dH dt is equal to 2 centimeters per second. Then it asks, at what rate, again a derivative, is water being poured into the cup when the water level is 8 centimeters? Okay, so the water level, or H, is 8 centimeters. And then what we're looking for is basically how fast is the volume changing? At what rate is the water being poured into the cup? So this is going to be dv dt. That is what we're trying to find. Okay, so now we want to ask ourselves what principal equation ties in everything together, the radius, the height, and the volume. Well, we're given a cone, so the volume of a cone is pi over 3 r squared h. Now notice that we have two variables here, but r is a constant value. And so if we have a constant value and we take the derivative of it, we're going to get 0, and we don't want that in our calculation. So we want to replace r with its relationship with h. Notice that r is equal to 10, and initially h is also equal to 10. So r is equal to h, and so we're going to replace r with h. So pi over 3 h cubed. Now we can take the derivative of this, d dt. So dv dt is equal to pi over 3 times 3h squared times dh dt. We can cancel out the 3, and we get dv dt is equal to pi, and then h, remember, is 8 for the situation right now. So h squared times dh dt is 2. And so dv dt is equal to 64 times 2, which is 128 pi. And then for our units, again, we're looking for volume here, so it's going to be centimeters cubed per second. That is our answer right here. The last example we have is one of a right triangle. So it says a 7-foot tall person is walking away from a 20-foot tall lamppost at a rate of 5 feet per second. Assume the scenario can be modeled with right triangles. At what rate is the length of the person's shadow changing when the person is 16 feet from the lamppost? Okay, so first of all, we have a person, and he is 7 feet tall. Okay, and then it's walking away from a 20 feet tall lamppost. So this is the lamppost. And then we also are given that the person has a shadow. So the shadow, realistically, if the lamppost is here, the light is going to reflect, and so the shadow is going to go to the left. So that's the shadow. And then it says that we can use a right triangle. So here we're really looking at the point of the shadow to the tip of the top of the lamppost. So that's the relationship here. I'm going to reduce this so it matches. But yeah, the person should be 7 foot tall. Here, let's make a relationship. So this length x is the distance from the person to the lamppost. Okay, and then this distance y right here is the length of the shadow. Okay, so it gives us that the person is walking away at a rate of 5 feet per second. So again, the rate tells us a derivative. The person, or the distance between the person and the lamppost, is increasing at this rate. So dx dt is increasing at a rate of 5. And then it also says, at what rate is the length of the person's shadow increasing? So at what rate is y increasing? So dy dt is what we're trying to find. Okay, and then we're also given that the person is 16 feet from the lamppost. So x in this situation is 16. So notice that we have similar triangles in this situation. We have the one for y and 7, and then we have y plus x and 20. So if we want to establish a relationship here, it's the best way to do so is through ratios. So the first one, 7 over y. The second one, we have 20 over y plus x. If we equate those together, then we can do 7y plus 7x is equal to 20y. I just basically cross-multiplied right here. Okay, so I'm going to move all the y's to one side. So we have 7x is equal to 13y. Now, this is our equation right here. We can derive this, d dt, to get dy dt. So on the left, we have 7 times dx dt is equal to 13 times dy dt. Okay, and then 7 times, so dx dt, we are given that it is 5. and then 13 times dy dt is what we're trying to find. Okay, so dy dt is equal to 35 over 13, and that is our answer. And so for the units, since we are basically only trying to find distance, it's going to be just feet per second. And yeah, that is our answer. So before I end this video, I want to show you guys some tips and stuff that helps for me. So first of all, in every related rates problem, you're working with a geometric shape. And so once you figure out the shape that you're dealing with, it's really easy to just sort of guide the rest of your calculation. So usually for two-dimensional shapes, you have either a right triangle, and the equation you use for that is probably Pythagorean theorem. So a, b, c, so a squared plus b squared equals c squared, and then you take the derivative of that. Or you have a circle, and so that would just be like the area is equal to pi r squared. You may have like a rectangle, that's just a times b. And then for three-dimensional shapes, you probably have a sphere like we worked with earlier. And then that volume is 4/3 pi r cubed. You might have a cone, and so like the one we worked earlier, the volume is pi over 3 r squared h. And for a cone, you want to make it so that it's in terms of one variable. The other one you might come up with is a cylinder, a circular cylinder. The volume for that is just pi r squared h. And so I recommend just memorizing these formulas because these are the most basic ones. Notice that for two-dimensional shapes, they mainly really only ask for length or area. For three-dimensional shapes, it's volume. It's just mainly volume. And so once you figure out the type of geometric shape you're working with and you recall that formula, it's really easy to just take the derivative of that and then plug in all the variables that you know and just solve from there. Another thing that you can use to guide you is units. So notice that volume, it's always units cubed. For area, it's units squared. And then for like stuff just like length, it's just units. And so when you know what type of units you're going to end up with for your final answer, you can use that to guide you. Just ask yourself, does this equation, do I multiply the right things to come out with the units that I want? Stuff like that. That can really help guide you to the right answer. So always remember that related rates is supposed to be fun, and if it's not, you're doing something wrong. Okay, so I hope this video helped, and I'll see you guys in the next one. Bye!